On September 23, 1999, a spacecraft reached Mars after traveling through space for more than 9 months. Its final maneuver had been planned for years. Its trajectory had been calculated again and again. Teams on Earth were watching as it passed behind the planet, where radio contact would briefly disappear. But the signal vanished 49 seconds earlier than expected. It never returned. The spacecraft had arrived at Mars on the wrong path. And hidden inside that path was a mismatch so ordinary that it could have appeared on a school worksheet. One system used English units. Another expected metric. But this was not simply a story about inches versus centimeters. It was a story about how a small error can survive inside a large organization until there is no time left to stop it. The Mars Climate Orbiter launched on December 11, 1998. Its job was to become the first interplanetary weather satellite, studying the Martian atmosphere, climate, and surface changes. It would also support another mission, the Mars Polar Lander, by acting as a communications relay. For most of its journey, the spacecraft appeared to be healthy. The trip from Earth to Mars was not a straight line. Mission controllers regularly estimated the orbiter's position and used small thruster firings to keep it on course. These tiny adjustments mattered. Across millions of kilometers, a small error could grow into a completely different arrival path. The navigation team at NASA's Jet Propulsion Laboratory in California depended on data produced by software connected to the spacecraft team in Colorado. The numbers passed between them described the effect of the orbiter's small thruster firings. The interface specification required those values to use metric units. They did not. The contractor's ground software produced impulse data in pound-force seconds, an English unit. NASA's navigation software interpreted the same numbers as Newton seconds, a metric unit. 1 pound-force is about 4.45 newtons. That meant each small correction was being represented incorrectly inside the trajectory model. The spacecraft was not suddenly commanded to turn 4.45 times too far in one dramatic moment. The effect accumulated through a series of small events during the journey. Imagine keeping a financial ledger in 2 currencies, but removing the currency labels. A number enters one system as dollars and leaves another as euros. Every individual entry still looks neat. The calculations can still run. The totals can still appear precise. But precision is not the same as correctness. With each adjustment, the estimated path and the real path moved farther apart. By the time the orbiter approached Mars, this was no longer a small bookkeeping problem. It was a navigation problem measured in kilometers. The most important part of this failure is that the incorrect unit did not operate in complete silence. During the flight, the navigation team observed unexpected behavior in the trajectory. According to NASA's later case study, anomalies in the ground software were discussed informally but not resolved. The investigation found weaknesses in communication, verification, training, and the way concerns moved through the project. There were opportunities to catch the mismatch. The delivered software could have been checked against the interface requirement. Independent calculations could have revealed that the forces did not agree. The unusual trajectory behavior could have triggered a more formal investigation. A final correction maneuver could potentially have changed the arrival path if the problem had been understood early enough. But no single safeguard stopped the error. This is why NASA officials resisted describing the loss as the fault of one careless person. People make mistakes. Complex missions are designed with reviews, tests, and checks because mistakes are expected. The deeper failure was that the system allowed a simple mistake to pass through all of them. On September 23rd, the Mars Climate Orbiter began its orbit insertion maneuver. If the spacecraft had followed the intended path, the engine burn would have placed it into an elliptical orbit around Mars. Instead, later calculations indicated that it passed the planet at an altitude of roughly 57 kilometers. That was far below the planned approach altitude and too low for the spacecraft to survive. As the orbiter moved behind Mars, controllers expected to lose the radio signal temporarily. That was normal. What was not normal was the timing. The signal disappeared 49 seconds early. Teams waited for the spacecraft to emerge and call home. Nothing arrived. The investigation could not determine with absolute certainty whether the orbiter was destroyed in the atmosphere or passed back out into an orbit around the Sun operationally. The result was the same. The mission was lost. Years of work had ended without a single orbit of Mars. The official investigation identified the root cause clearly. A ground software file used English units when the trajectory model required metric units. But a root cause is not always the whole cause. NASA's investigation also identified contributing problems. The project's verification and validation process did not confirm that the software met its requirements. Communication between teams was not strong enough. Navigation concerns were not handled through a formal process that guaranteed resolution. The end-to-end behavior of the system was not tested well enough to reveal the mismatch. The unit error explains how the trajectory became wrong. The process failures explain why it stayed wrong. That distinction matters far beyond spaceflight. A typo in a spreadsheet, an incorrectly labeled medical dose, a reversed engineering dimension, or a missing software assumption can begin as one person's error. Whether it becomes a disaster depends on the system surrounding that person. A resilient organization does not assume that nobody will make a mistake. It assumes that someone eventually will, and builds independent ways to detect it. The Mars Climate Orbiter is often summarized in a single sentence. NASA lost a spacecraft because one team used imperial units and another used metric. That summary is memorable. It is also incomplete. The mission was lost because a unit mismatch entered the system, because software did not enforce the expected unit, because verification failed to expose it, because unusual data did not lead to a resolved investigation, and because the full chain was not examined in time. The error was small. The distance it traveled through the organization was enormous. That is the pattern this channel will follow. Not just the final mistake, but the sequence of decisions that allowed it to become expensive. Because disasters rarely begin at the moment everything breaks. They begin earlier, when the first warning is recorded, misunderstood, or ignored. This is error ledger, the true cost of one wrong decision.